I've written a desktop app in C++ to emulate modern 3D API output like DirectX and OpenGL. I've used DirectX a lot and it's easy to use and you can quickly achieve the ability to render 3D primitives, but it does a lot of work for you, and I thought it'd be interesting to do all the work yourself, all the transforming, the clipping and the lighting. This is a brief overview video of the app and its functionality so far. So here we have the typical Utah Teapot. We're using per pixel lighting, we're using a directional light, and we're achieving about 1075 frames a second. As you can see, when we move the teapot around, there's no problems, there's no lags. We can scale it and rotate it and so on. That's a free rotation. You can rotate it around a bound axis, and it's very responsive, and I'm pleased with that implementation. If we change the scene to render the lights, you can see there is the actual directional light that's illuminating the scene, and like we could rotate the teapot, we could also rotate the directional light itself, and obviously that will impact on the scene. Here's another demo of materials. So this material has been bound to all the faces in the scene, and it's got a cubic environment map within it. So if we rotate this object, this is 100,000 faces on the dragon. It's got, like I say, a cubic environment map material associated with all the faces, and so it looks like it's reflecting the static environment that was rendered into the cubic environment map. Still very responsive and still very usable. This is another demo of the Stanford bunny. Now this has also got a material, but the material in this case has got a texture map associated with it, and the material is bound to all the faces in the model. So as you can see, this model is now using a texture map. Let's have a look at another demo. Oh, this is a bump map. So again, simple cube that's got a material bound to all the faces, and the material's got within it a bump map. If we rotate the light, we can see the effect the bump map's having on the lighting at different orientations of the directional light. Nice effect, and it's something that I wanted to implement. To make scenes more realistic, I also wanted to implement shadow maps. So here we've got a teapot behind the dragon, and the shadow maps are turned on for this scene. So if we've also got one directional light, and we can see that the shadow of the dragon is partially on the teapot, and if we rotate the light, we can see how the shadow is updating on the teapot. We can also see that if we rotate the object itself, we could also see the parts of the dragon are in its own shadow, which is quite a nice effect, quite interesting, and still very responsive and very usable, and just adds a level of realism to the scene. Here we've got a simple cube. Its vertex format includes color, so if we wanted to, we could use the UI to set up the color attributes at a particular vertex. So here we're changing face 0, vertex 0's color to blue. So let's change face 0, vertex 1 to red, and vertex 2 to green. And there we have the face. Instead of being all white, colour is interpolated across the face now, given that the three vertices that make up the face have got different colours, as you can see. So that works. Also supported is hierarchical structure of the scene. So here I've got a statue and an elephant, and I've made the statue a child of the elephant. So if I select the elephant and move it around, as you can see, because of the hierarchy in the composite transforms, the statue moves along with it. We could move the statue independently, but if we rotate the parent object or transform it in any way, you can see that the statue comes along for the ride. If we have a look at the scene UI, we could pick up that statue and make it a direct descendant of the scene rather than a direct descendant of the elephant. And now it's not a child of the elephant, so if we pick up the elephant, we could move it around. The two are completely independent of each other. So there's a few demos that give a brief overview of what we can do. It's nothing like the full capabilities, but it's a brief overview. So what were the goals in creating this app? Well, I wanted to support both DirectX and OpenGL paradigms. I wanted a flexible Vertex format, so any of the combinations of positions, normals, colors, bump maps, texture map coordinates can be stored at a vertex. I wanted a flexible, customizable render pipeline. That includes the vertex and the fragment shader. I wanted multiple light sources. I wanted a light source to be a spotlight, point light, or a directional light. I wanted per pixel lighting. I wanted materials support. I wanted a material itself to support colors, textures, bump maps, and cubic environment maps. To add a level of realism, I wanted shadow maps to be supported, and I wanted a model to have an opacity so it could be semi-transparent, and also a simple and small set of tools to transform models in the scene and lights in the scene and the camera itself. So they were rendering goals. The UI goals, really, I wanted the ability to import objects into the scene, effectively try and do all the heavy lifting. So import models, and then have a set of UI panes on the right, one being scene, one being light, one being faces, and one being materials. So these will let you alter the hierarchy of the models in the scene. They will let you change the attributes of any light selected in the scene, let you change the attributes of any vertex on any face in a model in the scene, and also let you bind. Oh, I wonder why that's done that. Here we go. Maybe that needs to be looked at. And also a materials pane that lets you add a material, delete a material, bind it to a specific range of faces, and once you've got a material that's bound to a set of faces, you can change the attributes of that material. So its color, its texture, its bump map, its cubic environment map, and so on. So all of this is multi-core aware. It's all really responsive, like a default scene with the standard Utah Teapot achieving over 1,000 frames a second. I was really pleased with, especially because it's per pixel lighting. And all of this is written in C++ and is available on GitHub. It comes with a default vertex shader and fragment shader. The default vertex shader will do all the transforming from model space to 4D clip space. It will determine whether or not a face is completely outside of the boundary of the clip cuboid. And the default fragment shader that you can use and customize knows to skip faces that have been deemed outside of the clip space by the vertex shader. It also knows how to clip if it's partially outside using Sutherland-Hodgman, and then it knows how to use barocentric fragment coordinates to determine colors and all various attributes at that fragment. And it's material aware and shadow map aware, and like I say, both the fragment shader and the vertex shader are multi-core aware, so all work is spread over all the available cores. So yeah, like I say, the details of the GitHub address will be in the description, and there may be some more videos in the future that are a bit more detailed about the UI and the C++ and the maths that went into the implementation.